Backward propagation. So the goal with backward propagation is to update the weight as well as bias in the network so that it causes our predicted value of y, that is the predicted output value, to be closer to the actual value of the output which is provided by our labeled data set. Or, in short, we are trying to minimize the error for each of my output neuron and the network as a whole. And in order to facilitate this backward propagation, we use the algorithm called as gradient descent. So as you already know, gradient descent is an iterative algorithm which is used to optimize. It is an optimization algorithm. And in our case, we use this gradient descent algorithm to optimize, in our case minimize, our total error of our network. So let's get started with the same network which we have used, and we have already computed its total error based on forward propagation. So let's get started. So let us start with backward pass. So this was the network which we have used in order to do our forward propagation. And using the forward propagation, we have calculated the total error of this network based on the fact that we have taken the W1 weight to be 0.5, W2 to be 0.20, and up till the weight W8 to be 0.55. So as I have mentioned, during the backward pass, we are trying to adjust these weight values so that the total error of the network becomes minimum. So let us first start with the first weight value, that is W5. So we have to propagate from backwards, that is like this. So that means the first set of weight we will be initializing is W5, W6, W7 and W8. Once we have done that, we will then update the weight in the hidden layers. So that is W1, W2, W3 and W4. So we will first start with this output layer and the weight that affects the output layer, which is W5, W6, W7 and W8. Of that, we will start with the first weight, which is W5. Now, what we wanted to know is, we wanted to know how much a change in W5 affects the total error. And it is represented by dou E total divided by dou W5. And this representation means that if I change the value of W5, so if I change the value of W5 by little bit, how will the value of E total change? And this is read as the partial derivative of E total with respect to W5. So this is read as the partial derivative of E total with respect to W5. And this is also called as the gradient with respect to W5. And this representation just means that if I change the value of W5 a little bit, then how would the value of E total change? Right? Now, what we do is, so we wanted to find dou E total divided by dou W5. So to find that, we will apply the chain rule. So you might be already familiar with the chain rule and derivation from your math course in the first semester. So E total, dou total by dou W5 is nothing but, I can write it according to the chain rule as dou E total divided by dou out O1 into dou out O1 divided by dou net O1 into dou net O1 divided by dou W5. So imagine imagine this is like a multiplication. So this OW1 and OW2 cancel out, this cancel out, and you are left with dou E total and dou W5, right? So this is how the chain rule works. So now we have the equation. We need to figure out each components of this equation separately, right? So let us get started with the first piece of this equation, which is dou E total divided by dou out O1, right? Now for that, we already know what is the equation of E total. So E total was nothing but half into target of O1 minus out O1, the whole square. So target of O1, it's nothing but the actual value of my node O1 minus out O1, which we have already calculated from our forward propagation, is nothing but the predicted value of O1, right, plus the same half target of O2, which is the actual value of O2 minus out O2 the whole square, right? So we have the equation for E total. So what we wanted to find is dou of E total divided by dou out theta 1, which is nothing but this piece of the equation, this piece in the equation that we are computing, right? So that is equal to, so again, I assume you are familiar with the partial derivation. So this is nothing but 2 into half into target of O1 minus out O1 raised to 2 minus 1 into dou by dou out O1 into target of O1 minus out O1 plus, and this so this entire thing is this particular equation derivation, and this will be nothing but equal to 0. So plus 0, this is equal to 0 because in this case there is no dou out O1 term in this equation, so naturally it will become as 0, right? So when I further do this, so this is equal to, these cancel out, so target O1 minus out O1, 2 raised to 2 minus 1 is 1, into dou by dou out of target O1 is 0 minus dou by dou out of out 1 is 1 plus, of course, this 0, which is 0. So it is nothing but minus of target O1 minus out O1, which is equal to minus of target O1, which is the actual value of output O1, which we know is 0.01, minus out of O1. So out of O1 is something which we have already calculated in the forward propagation, which is nothing but 0.7513657. So that would be equal to 0.7413657. Right? So this is the partial derivative of the first piece that goes into my equation for this, which is E total by dou out O1. Right? Similarly, I have to compute this partial derivative and this partial derivative. So next I need to compute the partial derivative of dou out O1 divided by dou net O1. Right? And if you already, so you might recall that out O1 is nothing but, it is 1 by 1 plus e raised to minus net O1, right? And if I take the partial derivative of this, it is nothing but out of O1 into 1 minus out of O1. So the partial derivative of this is nothing but this one, right? So I can just substitute the value. So dou out O1 by dou net O1 is equal to, out O1 is 0.75133650 minus 1 minus 0.75133650.7, and when I do this, I get the value of 0.186815602. Right? So that is also done. And then the final piece in this equation is dou net O1 into dou O5. So we need to next find out what is dou net of O1 divided by dou net of, dou W5. Now, from the forward propagation, we already know that net of O1, the equation was W5 into out H1 plus W6 into out H2 plus 1 into B2. So that is equal to dou by dou W5 into W5 into out H1 plus dou by dou W5 into W6 into out H2 plus dou by dou W5 into B2. So that is equal to, so from this it is out H1 into dou by dou W5 of W5 plus this part of the equation is 0 because there is no W5 in this equation, and this is also equal to 0 because there is no W5. So what you are left with is, this is equal to out H1, and we know dou W5 into dou W5 is nothing but 1. So we have found out dou net of O1 is equal to dou divided by dou W5 is nothing but out H1, and the value of out H1, which we have already found out from our forward propagation, is 0.593269992, right? And then finally we need to put it all together. So we need to find dou E total. This is where we started. We wanted to find dou E total divided by dou W5, which was equal to here, right? So this equation multiplied by this, and we already found dou E total by dou out O1, which is 0.74136. We already found dou out O1 by dou O1 to be 0.18685, and then we have already found the dou net O1 dou W5 to be this. So we multiply those three values, that is 0.74136507 into 0.186815602 into 0.593269992, and that is equal to 0.82167041. So once we have got this value, the next step is to update the weight of W5 using our gradient descent algorithm. So according to gradient descent algorithm, new weight is equal to old weight minus the learning rate alpha into gradient, which is dou E total divided by dou W old, right? So in our case, we are finding it for W5. So I write W5 plus, which indicates the new value of my weight W5 is equal to old value minus the learning rate alpha. So for the time being, I take alpha to be 0.5. Usually we don't give such high values for alpha, but just for the sake of easy computation, I write it 0.5 into the value which we have already computed, that is 0.821674041. So the initial value of W5 which we have assigned was 0.4 minus 0.5 into this value, and when you compute this you get 0.35891,648. So that is my new value of W5. Now we need to continue this same process for the remaining weights that affects my output layer, which is nothing but W6, W7 and W8. So we needed to find the same way, in a similar way, we needed to find what is the new value of W6, new value of W7 and new value of W8. So please try this at home. What are the new values of these weights? Now once we have figured out these values which affects the output layer, now we need to again do the same process for the weights in the hidden layer. So that is, if we go back to our network, the hidden layer weights are W1, W2, W3 and W4. So we wanted to find out this, we wanted to do the same procedure and find out what our W1 plus will be, new weight of W2, new W3 and new W4. So we will just pick one more weight W1 and try to do the same procedure and find out what our new weight for W1 will be. Next, we will continue the process of backpropagation for the hidden layer, which is this H1 and H2, and we will update the weights W1, W2, W3 and W4. To start with, we will pick the weight W1 and then update it. So again the process continues. So here I wanted to figure out how my total error will change with a small change in my weight W1. So as I have mentioned at the beginning, that is represented by dou E total divided by dou W1. Now applying the chain rule as before, we have dou E total divided by dou out H1 into dou out H1 by dou net H1 into dou net H1 divided by dou W1. So we will pick each of these components separately and then find what those values are and finally multiply it with each other to get what our partial derivative is, dou E total by dou W1. So let's get started with the first component of the formula, which is dou E total divided by dou out H1. So when we consider dou E total by dou out H1, we need to take into consideration its effect on both the output neuron. So we are talking about in this particular neuron, that is H1, we are considering how the out H1 will influence the value of E of total. So as you can see from this figure, this out H1 will influence this H, which is nothing but the EO1, and also influence this EO2. So we have to further divide dou E total by dou out H1 into dou EO1 divided by dou out H1 plus dou E2 divided by dou out H1, right? And for that again we will start with the first one, which is dou EO1 divided by dou out H1. Again applying the chain rule, this is what my formula will be, and I continue this process of my partial derivative. So I have solved this and I have got the value to be 0.1389 and so on. So now we have found out this particular component. It is now time to find dou net O1 divided by dou out H1. Now once we find this component also, we will multiply that together in order to find what is dou EO1 divided by dou out H1. Now once that is done, we have to find dou EO2 divided by dou out H1 and then add these two components together to find our dou E total by dou out H1. So next I find out So in the previous slide, see, in order to complete this component, I also need to find dou net O1 by dou out H1. So we will go ahead and find that dou net O1 divided by dou out H1. So I have found the partial derivative and I have got its value to be 0.40. Now after that, I find out dou EO1 divided by dou H1, again found the value. So once those two are done, I have found this dou theta 1 divided by dou out H1. I can multiply those two values. Now next I need to do the same procedure for dou EO2 divided by dou out H1. So here you can see I am finding dou EO2 divided by dou out H1 and I got the value to be this. So once I have obtained that, I find my dou E total by dou out H1, which is this value. So now we have found out this particular component. Now I need to do the same procedure for the second component of this equation and find out what dou out H1 divided by dou net H1 is. So here I have computed that. So dou out H1 by dou net H1. So for those who are not familiar with partial derivative, but I believe everyone should be, as you might have studied that in your math course. So if I have a sigmoid activation function like f of x is equal to 1 by 1 plus e raised to minus x, then derivative of that function is nothing but f of x into 1 minus f of x. Right? Now, dou out H1 is nothing but 1 by 1 plus e raised to minus net H1. So these are the formulas from our forward propagation. So it is nothing but, so its derivative is nothing but f of x into 1 minus f of x. F of x in our case is out H1. Right? So out H1 into 1 minus out of H1. So we get this particular value. And then after that, we have to find the final component of this equation, which is dou net H1 divided by dou W1. So let us go ahead and find that. Dou net H1 by dou W1, and once you do that partial derivative, you get the value to be 0.05. So since we have now found out all the components of dou E total by dou W1, the next step is of course to multiply all these values we have found out, and we have got this particular value. Once we have that, it is now time to update the weight using gradient descent, and again I am updating the weight W1, which is equal to my original weight or my previous weight, which was 0.15 for W1, minus the learning rate alpha, which I have taken to be 0.5, into E total by W1, which we have found out. So this is the new W1 we have obtained. And then I need to continue the same procedure to find the updated weight for the remaining weights in my hidden layer, which is W2, W3 and W4. Right? So once one iteration or one epoch of my neural network is done, I will have my first updated weights available. So similarly, we have to update the bias value also, B1 and B2, right? So once we have done our first iteration of our forward and backward propagation, we will now have the updated weights for W1 till the updated weights for W8, right? Now once you have this updated weight, using this updated weight, now you have to do your second round of forward propagation. Yes, using this updated weight. Now once again you do your forward propagation, what you will get is your total error. Right? You get your error, total error. And then based on this total error, what happens is that again the next or the second backward propagation happens. Second backward propagation happens, and again the weights of W1 up to W8 will be updated. I will be sharing this PPT document with you. so that you can go through each of the steps which we have discussed, and make sure to try this one out, and also pick one of the weights from both the output layer and the hidden layer, and then try to find the answer for that, to make sure that you understand now fully the concepts of forward and backward propagation. So to summarize what we have discussed, in forward propagation we find the total error, and during the backward propagation we are trying to decrease or optimize this error, so that our predicted output value by our neural network is as close to our actual output value. And during our forward propagation, we calculate the total error, and during our backward propagation, we will try to adjust the weight of our neural network so that our total error is minimized. And in order to do that, we use optimization algorithms. And the famous one, and the one that we have used in this example, is the gradient descent. So during the forward propagation, based on the algorithm that we have chosen to initialize the weight, so in this case we have used a random initialization. So in the first forward propagation, we will, or the algorithm will randomly assign weights for each of the layers, and during the backward propagation we adjust this weight and bias.